All right, so the other day we covered section 6.1. And section 6.1 was about multiplying polynomials. The truth is, as far as algebra is concerned, multiplying polynomials is really not a very useful thing. Very rarely do you actually ever want to multiply polynomials. So why do we teach it? Well, we teach multiplying polynomials so we can turn around and teach you unmultiplying polynomials. And the fancy word for unmultiplying is called factoring. So that's what we're going to start looking at for the next few sections. We're going to talk about factoring. And then at the end, we will talk about why do we want to factor. So that'll be later in the chapter. What's factoring good for? So, my guess is you have seen the word factor before. I might ask you, factor the number 24. And what would you tell me? One correct answer is 6 times 4. 1 and 24 is another correct answer. 2 and 12. 6, 2, and 2. I like that one. Nobody ever said that when you factor you can only use 2 numbers. 3. Yeah, you could go 1 times 1 times 1 times 1 times 1 as many times as you want. That's true. That's not very interesting, though. This is considered the most interesting factorization. Not because there's 4 of them.
It's the smallest it can go.
There's a word for smallest it can go. Not least. Begins with a P. Prime, that's correct. 3 and 2 are prime numbers, which means they cannot be broken down any further, except you can write 3 as 1 times 3, and you can write 2 as 1 times 2. Not very interesting. I think we skipped 8 and 3. That's a common one we used to. So this is called the prime factorization, quite often written this way, 2 cubed times 3. So in general, when we factor polynomials, we're always going to want to look for the prime factorization, which means we get to the point where we can't break down the polynomials anymore. There are a number of different techniques we're going to use for factoring, but today we're going to learn 2 things: the greatest common factor and difference of squares. So let's say I asked you to multiply. Let's say I asked you to take 2x squared and multiply it by 4x minus 5. What would you do? You would use the distributive property, and you would tell me the answer is 8x cubed, because you have 2 x's and 1 x, it makes 3 x's, minus 10x squared. The reverse of this is called factor out the GCF, where GCF is an abbreviation for greatest common factor. So it would go exactly the opposite way. We would start with 8x cubed minus 10x squared. And what we do is we look to see what do they have in common. So I look, I've got an 8 and a 10. What do 8 and 10 have in common? 2. And then I have an x cubed and an x squared. X squared. And then I put a parenthesis, and I think about, all right, now I got to use the distributive property. 2x squared times what will give me 8x cubed? 4x, and then minus, and 2x squared times what will give me 10x squared? 5. So factoring out the GCF is just completely the reverse of using the distributive property. That's all it is. All right, so let's take a look at some of these problems here. The voltage drop, V sub t, across 3 resistors in a series is given by voltage drop equals, what does R stand for in an electric circuit? Resistance 1 times, what's I? It's what? Current, measured in amps, typically. All right, so we have R1 times I plus R2 times I plus R3 times I. And over here we notice that we have one variable that's common to all three pieces. What's the one variable that's common to all three pieces? I. So we can factor it out, which means we put the I out front and we put a set of parentheses. And then again, thinking of doing the distributive property, what would have to go inside the parentheses? R1 plus R2 plus R3. Because now if I take that I and distribute it across, I get exactly what I started with that. Alright, so skipping down here. The apparent weight, W sub A, of an object submerged in a fluid is given by W sub A equals P sub M times V sub G minus P sub R times V sub G. The true weight minus the weight of the displaced fluid. Factor out the common monomial factor. It's, V sub G, I think this is supposed to be one variable. I don't think that's supposed to be V times G. I think it's V with a subscript of G. But either way, it's the common thing, isn't it? You could either say the common thing is V and G, or it's V sub G, depending on what it's supposed to be. I'm pretty sure that's supposed to be a subscript. So we would write W sub A. The common thing is V sub G. Then we put a parenthesis. What's left over? P sub M minus PR. All right. The total kinetic energy of a rolling wheel is given by E sub K equals 1/2 M times omega R quantity squared plus 1/2 M K squared omega squared. Factor out the greatest common monomial factor. You're telling me it's 1/2 M omega squared. Because I see a 1/2 in each piece, I see an M in each piece, and then there's an omega squared, a little hidden on the left one, but not too bad to hit. Alright, so I'll put a parenthesis. What goes inside? R squared, it's R squared because R squared is inside that parenthesis, plus K squared is all that's left over, I think, because we already have the 1/2, we already have the M, and we already have the omega squared. The only thing not written down is the K squared. Questions on that one? All right. The displacement of a uniformly accelerated body is given by X equals V naught T plus 1/2 GT squared. Factor out the greatest monomial factor. Yeah, it looks like the only thing common this time is the letter T, isn't it? There's a T here, there's a T there. Well, actually, there's a T squared there, but the common thing is only the letter T. So we factor out the letter T. Left over, V sub 0 plus 1/2 G and a T. Because if there was a T squared, we took one of them out front, which means there has to be one of them left over inside. Questions on that? When a bar of length L sub 0 is changed in temperature by an amount delta T, its new length will be given by L equals L0 alpha delta T, where alpha is the coefficient of thermal expansion. Solve for L sub 0. Oh, so slightly different. What does that mean when I say solve for L sub 0? Get it all by itself? Okay, so let me ask you if this would be correct. L equals L sub 0 plus L sub 0 alpha delta t. I'm going to take this equation and I'm going to subtract L0 alpha delta t on both sides. And so I would have on the left-hand side L minus L0 alpha delta t equals L0. Did I solve for L0? I have L0 all by itself on one side. Alright, so solving for L sub 0 means two things. It means you want L sub 0 all by itself on one side, and it can be the only one. I can't have L sub 0 stuck on the other side. So I didn't do any algebra mistakes here, but I haven't answered the question correctly. I have not solved for L sub 0. Alright, so it says solve for L sub 0 by first factoring out the greatest common factor. So when you see an equation like this, and you're trying to solve for L sub 0, and you see more than one of them, you need to factor it out first. So we're going to write L equals L sub 0, that's our greatest common factor. What's left over? One plus alpha delta t. Where did the 1 come from? Right, I need L sub 0 times something to give me that original L sub 0 back. Very common mistake to leave off that 1 right there. But I need L sub 0 times that 1 to get that original L sub 0, plus then the L sub 0 times this thing to give me that original term back. Don't forget about that 1. That's very easy to do. Alright, so now how would I get the L sub 0 all by itself? Divide by that whole mess there, right? So L divided by 1 plus alpha delta t. I don't know why I keep putting those parentheses. I don't really need them, but I'll put them anyway. Equals L0. So there's the correct answer. And that's what it means to solve for L sub 0. We have L sub 0 all by itself on one side, and no L sub 0s anywhere on the other side. Questions about that? Alright, and the other thing we have in here is called difference of squares. We saw this the other day. The other day we noticed if we took something like 4x minus 5 and 4x plus 5, and we multiplied those together, something interesting happened. What was interesting to me anyway. What was the interesting thing that happened? You only get the first and the last. The middle two added up to 0 and they went away. So we ended up with 16x squared minus 25. And we had a name for that. What was the name for that? Difference of perfect squares. Notice this is a square, 16 is a square, and then we have x squared, and 25 is a square. So now we're going to go backward. We're going to start with something like this and recognize that we have square minus square. So we'll factor it into two binomials like that. Oh, and then there was a name for these two things. Remember that? When these are exactly the same, but one has a minus and one has a plus. We did a hangman for that one.
Foil.
Not foil. We foiled them out to get the answer. But what was it called? Conjugate. Close. Conjugal was something very different. Conjugate. Conjugate, when these two things are exactly the same, but one has a plus and one has a minus. Those are called conjugates. Alright, so factor each of the difference of squares. Well, I notice I have 4r squared minus 16. What can I do with that? Two r plus 4, and the other is 2r minus 4. That's a pretty good answer. But I would say it's not the best answer. Can anybody give me a better answer? All right, so a better answer would have been, right from the beginning, I noticed there's a GCF. There's a greatest common factor. What's the greatest common factor? 4. If I take a 4 out, what's left over? R squared minus 4. And then I notice I have R squared minus 4. I have a square minus a square. So this is 4 times R plus 2 and R minus 2. So that would be considered a better answer. Whenever you go to factor, always look for a GCF first. If you can take a GCF out, take it out. Because notice that these two back up here that we had, 2R plus 4, there's a GCF there. What's the GCF on 2R plus 4? It's a 2. And then 2R minus 4, that also has a GCF. Its GCF is also 2. So I could write this as 2 times R plus 2 times 2 times R minus 2. And then I can multiply the 2's together. And I end up with the same answer in the end. But it's always better to take out the GCF first. All right, how about 81 minus 25y squared? Are those difference of squares? 9 minus 5y. 9 plus 5y, excellent. I sub 1 squared minus I sub 2 squared. I sub 1 minus I sub 2. And then the conjugate, good word. I sub 1 plus I sub 2. Excellent. In many problems, you will have to combine both the techniques. Well, we already talked about that. So, factor completely. 1/2 m v sub 1 squared minus 1/2 m v sub 2 squared. So whenever you see the word factor, the first thing you always want to look for is a GCF. Do we have a GCF? Yes, we do, and the GCF is 1/2 m. So I take 1/2 m out. Left over is v sub 1 squared minus v sub 2 squared. Then I notice I have square minus square. So that fits into our difference of squares pattern. 1/2 m, v1 minus v2, and v1 plus v2. Questions on that one? All right, the cross-sectional area of a hollow tube is given by A equals pi r squared minus pi r squared, where big R is the radius of the inside, and little r, or big R is the radius of the outside, and little r is the radius of the inside. Notice in math is actually case sensitive. When we use a capital R and we use a little r, those are considered different variables. And in this case, they explain specifically what the different variables mean. But even if it didn't explain that, if you had a problem with a big R and a little r, those are different variables. All right, so how would you factor that expression? Take a pi out. Big R squared minus little r squared. Okay. Correct, and then we notice it fits directly into the difference of squares formula. All right. How about the next one? I won't read the whole problem here. 1/2 g is our common. T sub 2 squared minus t sub 1 squared. And then again, 1/2 g. T2 minus T1, T2 plus T1. This directly into the difference of squares formula. All right, and then the last one. What would you do with the last one? Factor out an R? Sort of. Okay, so when I factor out the R, I have to be careful. It's kind of like in the previous problem when I factor out the 1/2. The 2 is on bottom, so the 2 needs to stay on bottom. The R is on bottom, so when I factor it out, it needs to stay on bottom. So I don't really factor out an R. I'm really factoring out a 1 over R. Since both the R's are on bottom, they have to stay on bottom. So I really factor out a 1 over R. And then, difference of squares, 1 over R. V2 plus V1, V2 minus V1. Questions on any of those?